Well, chaps, here we go. This is my first attempt at producing a recording for you, so forgive all the silliness and errors and mistakes that I make, and I hope you find it useful. So we're going to continue from the work on projectiles that we've been doing. Section 6.3, example 6 is where we're going to start, and I'm going to go through two examples, example 6 and example 7, and then set some work from the exercise at the end of it for you to try. At the end of which I would ask you to self-mark it. Okay, here we go then. A particle is projected from a point O on a horizontal plane with speed 28 meters per second with the angle of elevation 30 degrees. After projection, the particle moves freely under gravity until it strikes the plane at the point A. Find the greatest height above the plane reached by P, the time of flight of P, the distance OA. So the first things to notice are to extract the information from the question correctly. So if we have a look at that, what key information we got? It's projected from a horizontal plane with a speed 28 meters per second. Angle of elevation is 30 degrees, and it strikes the plane at the point A. So it's going to end at the same height at which it started. So our diagram is going to look like that. Its initial speed is 28 and the angle is 30 degrees. And it's going to land down at A at the same height. So just like with the work we've done on forces, we want to break this down into its two components. So we have a horizontal speed, which is 28 cos 30, because it's adjacent to the angle. And we have a vertical component of the speed, 28 sine 30, as it's opposite the angle and the speed is the hypotenuse. So when we're thinking about the greatest height that's been reached, we need to identify what the key facts are. So at max height, V, the final speed, vertically will be 0. U is going to be 28 sine of 30. A is equal to the acceleration, and that's going to be minus g. And we want S, the max height, which we can call capital H. Now, before I did all that, I forgot to say we should have considered the context. So here, we haven't got a formula, a function for the acceleration in terms of t. So we can work with it being as constant acceleration, and we are going to work vertically. And I've taken positive as up, so my acceleration is minus g. Okay, so now we look at the letters V, U, A and S, and we've got to state the equation that we want to use. So we're going to go through our usual structure, state, sub and solve. So when we state, we want the equation with V, U, A and S, which is V squared equals U squared plus 2AS. V squared is 0. U squared is 28 sine of 30 squared plus 2 negative g h. Taking care to substitute everything in a bracket as usual. So now we've got to work that out. 2gh gets added across. What we do to one side, we do to the other. Square out 28 sine 30. Well, that's 28. Sine of 30 is a half, and that's squared. So h equals 14 squared over 2g, which is equal to 14. That can't be right. That's nonsense. 14 squared is 198. Oh, wrong pen. So 14 squared, 198 over 2g. 198, did I say? That's 196. Whoops. Get the right things going, having to learn to use a new piece of software. So that's 196. So that's 98 over g, which we know is 10 meters. So that's part A complete. The time of flight, part B. So again, key things to think of at the time of flight. Because we finish at the same height that we leave, the time of flight is going to be twice the height to the highest, twice the time to the highest point. So time of flight is twice time to the highest point as the plane is horizontal. Oops, something strange happened there. As the plane is stopped working. As the plane is horizontal. So again, we're going to be using CVAT. It's constant acceleration. Define our positive, again vertically. Speed at the highest point is 0. U, because we're going vertically, again is 28 sine 30. A is equal to negative g because it's acting downwards, and this time we want the time of flight, which we'll call capital T. Our usual structure, state subsolve. So VU, A and T, the equation we need is V equals U plus AT. Substitute in the values, 0 equals 28 sine of 30 plus negative g capital T. And now we can solve it. So GT equals 28 sine of 30. So T equals 28 sine 30 over G. So total time of flight, and don't forget, don't forget, this is time to the highest point, therefore need to double. So time of flight equals 2 lots of 28 sine of 30 over g. So sine 30 is a half, so 28 over g, that's going to be just under 3. So sounds like about 2.9 seconds. Okay, that's that one done. Part C, which said the distance OA. So here we're going to be using CVAT horizontally, so constant acceleration. We want the distance OA, which is a horizontal distance, so we're going to be working horizontally. And here we have to remember that there's no acceleration. Yeah, whoops. Again, software learning. No acceleration. Yeah, as gravity is only force acting which is in the vertical direction. That's the key. So, as long as we've got that idea sorted, we know that A is equal to 0. We know how long it's in the air for. T is equal to 2.9 seconds. I'll use the exact version of it when I'm calculating it later. U is constant, and if we go back to our diagram, the horizontal speed is 28 cos 30. So U is 28 cos 30, and we want the distance S, which we can call R for the range. So the equation here then is S. So back to our state subsolve, S equals UT, and we don't really need the plus half AT squared because we know already that the acceleration is 0. So distance is equal to speed times the time. So R equals 2 lots of 28, 2 lots of 28 sine, oops, writing's gone wrong. Let me just scroll this up a little bit to give me space. So 28 sine of 30 over G times U, which is 28 cos 30, times 28 cos of 30. Okay, so we already know that what have we worked out already? Nothing there particularly. So we've got to simplify that down, and probably just best to tap it in a calculator, and we get 69 meters. I hope that's helped, and that's the first attempt at doing something like this. So any of your feedback on terms of structure and approach that I've used would be helpful. Okay, cheers.